Available, but the other one has 10 attempts available. So you can do either one. The one with 10 attempts might be better. So, but either one is fine. It doesn't matter. But I will take the highest score. So if you haven't started yet, do the one with 10 attempts. Okay. Well, let's um let's start by talking about um race cars. All right, so we've talked a lot about friction so far, and we've also talked about centripetal acceleration. So both of those, why is my camera? All right, so um, both of those things are important when we're talking about race cars. Race cars usually go around a track, and they often have a banked curve, sort of at some angle like this. Okay, so you've probably seen in NASCAR when the car is going around the corner, there's some angle like this, and this is so that the car can actually go faster around the corner and it doesn't slide off of the track. Um, and that's really important if you're a race car because if you go around a corner too fast, then you will slip off the road. What's the condition for when you start slipping if you're going around a corner in a race car? So let's say if I'm going on a curved track like this, what is the condition for when I would start to slip? So let's say this is just flat. So on the road. There's no curvature at all in the road, and I'm just going around in a corner. When would how could I find the maximum speed? Well, let's start by taking a look at that. Okay. So let's say we have some radius of curvature here, R, and we want to know at what point will my race car slide off of the road, okay? Because as I'm going around here, there's going to be um, centripetal acceleration. So the race car is going to experience mv squared over r. Now, if there's no bank in the road whatsoever, then um, there's got to be a force that's keeping me on the road. Otherwise, my car would just slide right off the road. Maybe this has happened to you if it was snowy. It happened to me one time when it was snowy outside. I was driving and my tires had very poor traction. I went around a corner and I kind of started to slide off of the road, and it was really scary because the only thing that's keeping you on the road is the force of friction. Okay. And so I've got a negative sign. Yeah. So the force of friction is keeping you on the road, and it's the thing that's going to be pulling you this way. And so if your centripetal acceleration is higher than the maximum static force of friction, you're going to slide off the road. Okay. And so let's put some numbers in here. And F of S is going to equal uh, the force of friction is equal to the coefficient of static friction times the normal force. And our normal force is going to be right here. That is our normal force, N. And that is um, how much the road is pushing up on the car. Okay. So um, then we can find, um, so let's solve for um, the maximum speed that we could go before we started slipping off the road. So let's see. We've got mv squared over r is going to equal mu s times mg. So our m's are going to cancel out, and then we'll have v squared will equal uh, mu s times r times g, and we can take the square root of that. So if we take the square root on both sides, then we will get v equals mu of s times r times g, and that's a square root. Okay. So if we exceed this speed, you will slip off the road. So depending on how sharp your turn is. So if R is smaller, then that means that your velocity is also going to need to be smaller as well. Okay. Um, so we could calculate our maximum velocity. Let's say that if R was 209 meters, we'll say R is 209 meters. We don't really need to know the mass of the car. Okay. And let's see, let's say our velocity V is 60 kilometers per hour. Okay. Then we can find well, we need to know the coefficient of static friction between the road and our tires. Does anybody know what it is off the top of their head? Otherwise, I can look it up. Let's see. All right. Coefficient of friction between road and tire. All right, so it's about zero point 0.8. So mu s is 0.8. And that's if it's dry. So it's between zero point 0.7 and zero point 0.8. This is if we are dry. But if the pavement is wet, this actually becomes zero point 0.4 to 0.6. Okay. So when the road becomes wet, our coefficient of static friction drops, and so that's going to also decrease our maximum velocity. But uh, given our turn here, let's put in some numbers. So we'll say that this is going to be the square root of, and we'll say 0 0.8, that's kind of the maximum, times our radius here. This will be 209 meters. That's the radius of our curve here. And then, of course, gravity is 9.8 meters per second squared. Okay. And the coefficient of kinetic friction does not have any units. And so when we take the square root of this, inside of our radical here, we'll have m squared over s squared. And so when we take the square root of that, we end up with um, meters per second. Okay. So let me calculate this real quick in MATLAB. Unfortunately, I don't have my awesome pink calculator right now, but we'll have to make it do. Um, well, let's say that this is about, we'll call that about 10 and, well, all right. Well, MATLAB is loading right now. But for the next part, we're going to start thinking about what if we add a bank to our turn here. Okay. The advantage of banking the turn is that when you're your normal force, so here's your normal force, okay, is coming off like this. Well, the the force of gravity is pulling you down, okay, so this will be m times g, okay? But the normal force now is actually going to have a component. If I draw my triangle like this, okay, then there's going to be a component of the normal force that's directed inwards towards my circle, okay? And that's a good thing because now if the road is banked like this, oh, somebody wants to get in. Okay, there we go. So if the road is banked, then that means besides just friction keeping you on the road, right? Because as you're going around this corner, there is going to be the force of friction is going to be pulling you this way. There's going to be a component of it pointing towards the center. But now we've also got a component of our normal force that's going to be pointing towards the center. Okay, so we'll call this NX, and this will be NY. Okay, so and that's a good thing. And so that's why whenever you go around a corner, especially on racetracks, the corner is always banked. There's always some angle here because you never want a car just driving on a flat corner because it's much easier to slide off the road. And there's a limit to what the amount of friction you can get on a road is. So, the coefficient of kinetic friction, that just depends on the materials. And for asphalt, this can range anywhere from zero point 0.6 to zero point 0.8. And you really can't change this because you're talking you can't change this because this is the properties of the atoms of the rubber and the road and when they meet together. So the only other thing that you can do is you can add this bank, and that's going to keep you on the road. And this is much safer. Even freeways, normal freeways, when you're driving, you'll notice that the corner is usually banked a little bit. All right, well, let's go back to my calculation here because my MATLAB has loaded now. So let me just plug in the numbers. Okay, so I'm gonna have the square root of the square root. I need a bracket. So the square root of zero point 0.8, that's the coefficient of kinetic friction, times 209 meters, and we're calculating what's the maximum speed that you could go around this corner without slipping off. Okay. All right. So I'm gonna hit this. Okay. So that gives me 40, looks like 40 meters per second. Okay. So let me go back here and I will record that. And so it looks like the maximum speed is going to be uh 40 meters per second if I did my calculations right, but I think I did. Okay. Uh, and what is 40 meters per second and miles per hour? So that's about 980, it's 89.5 miles per hour. Okay. So what we found here is that if the road has no bank and we've got this 209 meter radius of curvature, then the most that we can go by is about 90 miles per hour. Okay. Now, our freeways were actually designed to travel on safely at 150 miles an hour. Okay. So that means um, we're for a normal freeway, if for it to be safe, you're going to need to add a little bit of a bank there. Okay. And let's look at what happens real quick if this goes to if it gets wet. So let's say it's snowy and it's wet. Um, so if it's snowy and it's wet, I'm going to get my original calculation back here. And let's see. Let's change that to 0.4. Okay. So that is 28.6 meters per second. And I will go to my online converter. So when it's raining or snowing outside, then that means that basically uh, this would be for rain or snow. This is going to drop, and so I can only go 28.6 meters per second, or about 64 miles per hour. So 64 miles per hour. So when it's wet, it drops off pretty quickly. But let's see what happens when we add a bank to our turn. So we're going to add a little bit of an angle here. Okay. So we need to think about our forces now. Okay, so let's go back and we'll draw another picture. All right, so I'm gonna tear this page off. All right, this one goes over here. Okay, so now, oh, and I had the diagram over here. All right, so I've got my normal force here, and I want to get this component because this is going to be part of my centripetal acceleration. This is also going to help keep me on the road. Okay, so let me.
She has
All right.
been blowing up my phone, and then I text her, and she's radio silent. We have cinnamon and lemon curd.
All right, I'm gonna
Caramel sutra.
all right, I'm gonna if you have a question, feel free to unmute yourself, but um if you don't have a question, uh please just keep your mic muted here. Okay, so let's talk about our forces here. All right, so we've got our normal force and our normal force going down the hill, okay? Normally our normal force here, Fn, that's going to be the hypotenuse of our triangle, and we want to get this opposite side here. And so let's think about the forces pointing towards the center. Okay, so um, my normal force pointing towards the center, if Fn is we'll call that the hypotenuse of my triangle, okay, then I'm going to I'm going to say F of n times sine of theta because I've got my angle here. This is going to be theta. And this angle is going to be the same angle as my triangle here, theta. So if I know what theta is here, I also know what this angle theta is here. Okay. And I've got f of n times sine of theta, and this is going to equal uh, my centripetal my centripetal force. So that's going to be the force keeping me in the center. Okay, so let's see what this force is equal to. Okay, so this is m times minus v squared over r. Okay, and so this is basically my force here. Okay, so it's pointing towards the center, and that's a component of the force up here. Okay, I've also got my normal force, okay, because well, I've got the y component here of my normal force, which is going to be equal and opposite to the weight of my vehicle. So for this part of the triangle, it's going to be f of n times cosine of theta, and this is going to equal m times g, okay? Because my force is down here equal my force is up, and so I can set these two equal to each other. And if I'm going around the corner, then um, the uh, the road having this curve here is going to give me some force pointing towards the center. Okay, so now um, now what I'm going to do is I'm going to get an expression for this. Okay, so I'm going to divide both of these together because I want to figure out what angle do I need to have here, right? So what angle do I need for my expression, right? In order for this to be safe. All right, so I'm going to divide these two expressions. I'm going to say f of n times sine of theta uh, divided by f of n cosine of theta is going to equal m um, m times v squared over r. And then down here, I'm going to have m times g. Okay, so my forces here are going to cancel. And then my m's here will also cancel. And I'm going to get, this is going to be tangent of theta is going to equal v squared over r times g. Okay, so if I want to get the angle, then I can take the arctangent of both sides of my triangle. And so I will get uh, theta is going to equal the arctangent of v squared over r times g. Hey, so now I've got an expression here for my angle. Okay, let's just pause for a minute. And does anybody have any questions about any of this that we've done so far? Because one of the homework problems actually has something in it very similar to this one. So, um, does anybody have any questions? You can put your questions in the chat anonymously if you want. And I can just read it. Let's see. Is anybody? Okay. Well, I don't see any questions, but um, let's let's look at let's look at a problem. Okay, I'm going to share my screen. All right, let's take a look in the textbook. If you haven't looked in the textbook, there's a lot of really good information in the textbook and a lot of really good examples that they have worked out. Okay. So I always say it's a good idea to read the textbook if you can. Hopefully, by this point, you have finished reading through chapter 6. And because we will be moving on to chapter 7 next time. Okay, so let me start reading here. Here the tract is banked, so the tilt of the normal force, and oh, here's a problem. Okay. When the highway is dry, the frictional force between the tires and the road surface may be enough to prevent sliding. When the highway is wet, however, the frictional force may be negligible, and banking is then essential. Okay. So if the frictional force on the track is negligible, what bank angle prevents sliding? Okay, so that's what we're trying to figure out. We derived this expression, but let's get some actual numbers here. Let's say the car is going 20 meters per second. Right, so 20 meters per second, that's about 50 miles an hour. Let me stop sharing my screen. All right. So if our car is going at, let's say, v equals 20 meters per second, and the radius of our turn is 190 meters and gravity G equals 9.8 meters per second squared, then what is the angle that we need to bank our road in order to keep our car from sliding off if it's wet? Okay, well, um, it looks like they calculated the answer to be about 12 degrees. So, all right, that's good. Now let's take a look at let's do a problem, okay? Because now we've got an expression, and so um I put online there is go to the assignments in Canvas, and I have added a couple of problems. Uh, and so let's take a look at some of the problems. And I want to solve some of these problems because they're very similar to the homework problems, right? And let's start by looking at one that's similar to what we're doing now. Let's see, put this. Okay, well, I guess let's start with number one here. Okay. A baseball player with a mass of 79 kilograms sliding into second base uh, is retarded by a frictional force of magnitude 490. What is the coefficient of kinetic friction mu k between the player and the ground? All right. So why don't we take about 2 minutes? Everybody start working on this problem, and then we will let's meet back together, and we'll go through it real quickly. Okay. So right now, take a let's spend 2 minutes, and we'll start working on this problem. And does anybody have any questions so far about anything that we've done, or just anything about physics at all? Well, okay, maybe about 30 more seconds. Okay. Well, does anybody have any questions about this one, or should we just go through it real quick? Any questions? All right, I'll check. I don't think anybody put anything in the chat. All right, well, let's just do it real quick. All right. Uh, So the baseball player has a mass of 79 kilograms, and he's sliding into second base, and there's a frictional force of 490 newtons. So I'm just going to draw my baseball player here. He's going to be like a squiggly line. Okay. And he is sliding into second base. Oh, and he's going the wrong way. Oh well. Well, he's he's going this way. All right, we're looking at it upside down. That's fine. Okay. So his mass is 79 kilograms, and the frictional force F of S is 490 90 newtons. Okay. And so what equation should we, oh wait, somebody's trying to get in. Oh no, I didn't let him in. Okay. I wasn't quick enough. All right. Which equation should we use to solve this one? Someone tell me. What is the equation for friction? Or put it in the chats. Well, all right. The only force acting on this guy to slow him down is going to equal the force of kinetic friction is going to equal mu of k times m times g. That's exactly right, Lily. Oh, I probably should. Sorry. Oh, yeah, you said it out loud. Okay. So that's right. Okay, so we can solve for mu of k now because we know everything else. We know what g is, we know what m is. Okay, so then this will be mu of k is going to equal f of k divided by m times g. And I will put the numbers in here. Let's see. The frictional force is 490 newtons, and the baseball player's mass is 79 kilograms times 9.8 meters per second. Okay, so he's sliding. And let me share my screen. We'll go to MATLAB real quick, and I will put these numbers in. So we have 490 divided by 79. How fast can I type it in? 9.8. And so it looks like the force of kinetic friction is going to be, I'll write that down real quick, 0.6329. All right, let's put it in and see what we get. Oh, somebody's trying to get in. There we go. Hello. Sorry, I think you were trying to get in before, and I I was too slow, and I apologize for that. Okay. All right. Well, you're in now, but all right. So let's go back to our problem and type in our answer here. And oh, sorry, what were you gonna say?
I just said thank you.
Okay. Were you waiting a long time or?
Oh no. Thanks.
All right. So I got 63.29, but I think that's too many significant. Well, I guess there's three significant digits, and then units. There were no units because it's static friction. Okay, let's see what the answer is. Okay, we got it right. All right, let's go on. Let's try and get through as many of these as we can, because they're fun. All right, the mysterious sliding stone along the remote racetrack Playa in Death Valley, California. Stones sometimes gouge out permanent trails in the desert floor as if they had been migrating. For years, curiosity mounted about why the stones move. One explanation was the strong wind during the occasional rainstorm would drag the rough stones over the ground. Okay. According to measurements, the coefficient of kinetic friction between the stones and the wet playa ground is 0.635. What is the horizontal force needed on a stone of typical mass of 16 kilograms to maintain the stone's motion um, once a gust has started moving? Okay, so this one's pretty similar to the last one. Nice. Let me draw a picture here. So let's draw our these weird stones. They move like this, and nobody knew how they were moving. Okay, here's our stone. And so what does the problem give us? We know, okay, they measured the coefficient of kinetic friction. They said that this was 0.635. Okay. And the stone's mass is M equals 16 kilograms. Okay. Well, then if we want to calculate what the force is to keep it moving, we're just going to use the same expression that we did before. So mu k times M times G. And I'll just put that into MATLAB. And maybe we need to, I guess I picked the problems too easy, but that's okay. All right, so we're gonna say 0.635 times 16 times 9.8. Okay, so the force, okay, so that is, write that down. We need a force then from the wind of 99.5680 newtons. And of course, that's way too many digits. So we're gonna have to get rid of those. Okay, so let's go back to our problem here. And to share my screen. And I got, let's see. All right, first of all, it's a force. So we need a newtons. And then I got 99. How many? Oh, we've got, well, we only have 16 there. So that looks like two significant digits. And if I round up, that should give me 100. What does this serve? Oh, my answer is partially correct. Okay. So I'm going to say 99.6. Okay. What's there we go. All right. Well, all right, I had 10 attempts. So it's fine. Okay, let's go on to another one. That one was too easy. Let's find something harder. Oh, all right. Oh, the coefficient of static friction between Teflon and scrambled eggs is 0.059. I don't know about you, but I love cooking eggs. Man, I don't know about Teflon though, because they're finding out that Teflon has these like forever chemicals. But it's nice. But anyways, don't worry about that. All right, what is the smallest angle from the horizontal that will cause the egg to slide across the bottom of the Teflon coated skillet? Okay. That's a good, I like this one because there's an angle there. And let's look at the coefficient of kinetic friction. It's 0.059. That is very low because when the rock was sliding on dirt, it was 0.635. Okay, so here, let's draw the picture of our egg. Hey, because not only do I like to eat eggs, but I like to draw pictures of eggs too. Here's my skillet. What a beautiful skillet. Here's my egg, and then here's the yolk of my egg. Okay, so I'm gonna lift my skillet up, and it's gonna start to slide. What angle do I need to get it at? Okay, well, all right, let's draw our picture of an egg. All right, we're gonna draw an egg on an inclined plane. Wow. I didn't ever know I'd be saying that sentence, but here we are. So here's my egg on an inclined plane. All right. Welcome. Oh, wait, he didn't. Okay. Welcome, John. I hope that you weren't waiting for very long. And I apologize if you were. We were discussing what is the angle here that where my egg, which is on an inclined plane, which is my skillet, will start sliding. Okay. Now, I don't know what the mass of an egg is, but I suspect that we don't need to know what the mass of the egg is. Okay, so let's talk about our forces here. All right, we're going to have our normal force this way. This is the force of gravity pulling down on the egg. This is m times g. We don't know what m is. I could look it up, but I don't think we actually need it. And then here, okay, this is our normal force. Okay, so that's our normal force. And we're gonna have this part of our triangle. Okay, so our angle here is gonna be the same. These are similar triangles. We're always using the same triangle. And then oh yeah, so we want this. We want the angle to, yeah, there we go. Okay. Well, let's see, what am I doing here? All right, you know what? I need to draw another picture because it's too small and I'm messing up my triangles. Oh, this is what happens. Okay. Here's my triangle, and here's my egg sliding down the Teflon. So here's my, this is my angle, and then the weight of the egg is going down this way, and my normal force is going to be like this. Okay, so it's like that. And then I have this part of the triangle. Oh, and I have I'm not drawing this right. Why? Okay, well, anyways, so here is our maybe I need let's make it a steeper angle. This. Okay, let's pretend our angle is like this. Okay, so here's my normal force, and I guess it is like that. Okay. Now, normally, all right, well, let's just solve the problem. Okay, so this part, ah, yeah, I think it's like this actually. Okay. Well, um, here is my, yeah, here's my triangle. I'm gonna say that positive X is going down this way. Okay. And so I can draw another angle here. These two are gonna be the same. I'm just having trouble today with my angles. Okay, so I want this part of the triangle because it's pointing down the hill. I had to convince myself in my own mind. And that's a right triangle right there. Okay, so the hypotenuse of my triangle here, that is my normal force, F of n, and then I want to get this part of the triangle. Okay, so just like before, we're going to use the same triangle, and I'm going to say that F of n times sine of theta, right? This is going to this is going to be the force pulling me down the ramp. And when it is equal to the maximum static force, the maximum force due to static friction, the egg is going to start to slide. All right, so this is going to be static friction here. So I'm going to have F of n times sine of theta, and this is going to equal mu of s times m times g, right? So, yeah. So, what was the problem asking for? Okay. So, what is the smallest angle from the horizontal that will cause the egg to slide across the bottom of the coated skillet? Okay. So, oh, now here I don't know what f of n is, but I know what this part of my triangle is, right? So I have this part. Um, so for this part of the triangle, that's going to equal f of n times cosine of theta, which is going to equal m times g. All right. So from this, I can get what f of n is. Okay, so let's try and solve this. Okay, so I'm going to say that f of n is, I don't know what my angle is, but this is going to be m times g equals cosine of theta. Oh, and let's actually look at these two, okay? So if I divide these two, right? All right, so here's what I'm going to do. Now it makes sense. I'm going to take this expression and I'm going to divide it by this expression. We've only got a few more minutes, so I think we can do it. So we'll have f of n times sine of theta equals mu of s times m times g. And then I'm going to, over here, it'll be f of n times cosine of theta. And then over here, I have m times g. Okay. So m times g divide over here. This is f of n. Okay. So this force goes away. These cancel. M times g cancels. And so it looks like I end up with tangent of theta equals mu of s. Whoa. All I needed to know was the coefficient of static friction, right? Because that's all they give us in the problem. So this angle I can find now. I'll take the arctangent of both sides. So it's going to give me theta is going to equal arctan mu of s, and they gave me that in the problem, and it is 0.59. So let's see, this is going to be arctangent of 0.059. Oh, somebody's trying to get in. Oh, hello there. I'm sorry if I made you wait for a long time. I apologize. Okay. Yes. So we are doing a problem where we're finding the angle which an egg will start sliding in a Teflon pan. And they only gave us the coefficient of static friction, which apparently is enough. Okay, so we just need to take the arctangent of this number, and that should be the correct answer. So let me go to MATLAB, and we will say arctan of 0.059, and what's, yes, I did mean arctangent. Okay, and that is 0.5089, but this is in radians, and so I'm actually gonna put it in degrees here. Okay, so in degrees, that angle is gonna be 3.3765 degrees. Okay, so that's gonna be 3.3765 degrees. And let's go back to the problem, and we will put that in, and let's see if we're right now. Yeah, it's in degrees, I'm gonna say, and so this had two significant digits, so it's gonna be 3.4 degrees, and we did it. Okay.
Thank you, like and subscribe down below.